It's a T.
It's a tau, yeah.
It's a tau. Capital tau.
That's scary.
Okay, nothing to do with topology, don't worry.
Is it torque?
Yeah, it's just torque.
So it's not that.
As you all know from reading the chapter, so you've been drowning in that symbol.
Of course.
And so you're very used to it. Okay, this upcoming chapter is considered one of the hardest chapters that you cover first semester. Probably the hardest chapter that you cover. I guess first semester, I mean for the year for us.
Yeah.
Because we're doing a semester's worth spread over a year. So consider a very hard chapter. But if it makes you feel any better, the next chapter is considered one of the easiest chapters.
What's
so
the
you have
chapter
that to look
after
forward to. Huh?
What's the chapter after this one?
Systems in equilibrium.
Okay.
But, so for this one, what have we been doing for the past couple chapters? We've been coming up with the rotational analog for linear motion. So, rather than talk about our position as an x-coordinate, or some system of coordinates in 3 space, we've instead been using theta to talk about our angular position. And instead of talking about our linear speed, we've been talking about our angular speed. And instead of our linear acceleration, our angular acceleration.
Which is velocity and speed are the same.
Speed is the magnitude of your velocity.
Yeah, I'm just saying.
So velocity is a vector, but
the word.
pretty close to same. And I'll accidentally use an interchangeably. But yeah, so you have your linear speed, your angular speed, your linear acceleration, your angular acceleration. And then mass, remember our intuition for mass was kind of like how hard it was to get an object moving linearly or stopping if it's already moving linearly. And our counterpart that we came across with 2 weeks ago, or 2 classes ago I guess, was moment of inertia. Moment of inertia was intuitively how hard it was to get an object spinning, or if it's already spinning, to stop it from spinning.
That's right.
It's like its resistance to spin, the same way that mass is its resistance to move. And that was just defined to be the sum of all the masses times their distance from the axis of rotation squared. And so the more spread out the mass is, the harder it is to spin it. The more concentrated the mass is, the easier it is to spin it. If I'm holding a big 2x4, if I'm spinning it this way, that's real easy. If I lay it out long ways and I try spinning it, it's much harder. Long board? So the axis that you spin it around matters, and how the mass is distributed relative to that mass matters. And then we talked about kinetic energy. Here's the kinetic energy for just linear motion, 1/2 mv squared. And we derived this last time. What's the kinetic energy for rotational motion? It's 1/2 moment of inertia times your linear speed squared. So those are our close analogs. Okay, so what we'll be introducing today is our analog for force, which we're going to call torque. In the same way that force, the magnitude of our force, is just mass times acceleration, the magnitude of our torque is just going to be moment of inertia times our angular acceleration. And we're going to be introducing a notion of angular momentum. In the same way that linear momentum was just mass times velocity for its magnitude, angular momentum, its magnitude, is just going to be moment of inertia times its angular speed.
Okay.
And then when we were talking about the work done to push some object, some linear displacement, then in its simplest case, right, if I'm just pushing with a force and I go 10 meters, then it's just F times that displacement of 10 meters. In its simplest case, that work done to get linear motion was just force times displacement. We'll see that the work done to get some rotational motion is going to be torque times its angular displacement. Make sense so far? So trying to help you have a way to just keep these formulas in your head so that you don't have to remember a ton of formulas and memorize a bunch of stuff. Trying to get you to see the relationships between the two. M's acting like I's, A's acting like alphas, B's acting like omegas, torques acting like forces. And then what's the relationship between them all? Well, the relationship between them all, it turns out, is multiplied by r. To get my linear displacement, I take my angular displacement and I multiply by the radius. To get my linear velocity, I take my angular velocity and multiply by the radius. To get my tangential acceleration, remember, not the one that goes into turning you, but the one that goes into actually speeding you up or slowing you down. We're now talking about centripetal acceleration. Remember our formula for centripetal acceleration? Or you guys use RAD, radial acceleration? That was v squared over r.
Yeah,
or omega squared times r. Same thing. So not that one. Oh, I wrote there just to make it clear it's not that one. But our acceleration, our linear acceleration, or acceleration that's going to speeding you up or slowing you down, was just alpha times r. Mind you, not the same thing as radial acceleration. It turns out our torque is going to be equal to our radial force times r, its magnitude. And it turns out that the magnitude of our linear
Momentum.
of our angular momentum, that's why I screwed up. The magnitude of our angular momentum is going to be equal to just the magnitude of our linear momentum times r.
Sweet.
So it's going to have those relationships. And so you'll see all this fall out as we go. So that's some of the stuff I want you to keep in mind, big picture, to help you remember all this. Because I think half of what makes it so difficult, maybe not half, but a chunk of what makes it so difficult, is just all the new symbols. And it gets hard to keep track of what's talking about what. So I don't want you to feel like you have to just memorize a ton of equations. I want to make these relationships appeal to your intuition. Okay, so with that, let's introduce now torque. Torque is, we can kind of think about it as the force for creating rotation. Forces create accelerations in the linear direction. Torques create accelerations in the rotational directions. They get things spinning.
Okay.
And so, if I were to go pick that door over there, and I want to open the door, I've got to create some sort of torque to get the door to rotate. I'm not actually kicking the door down and linearly displacing the door. I'm just rotating it about some axis of rotation.
Okay.
And you'll notice, where's a doorknob placed on a door?
The furthest out.
As far away from the hinges as you could possibly get it.
It's easier.
Because that makes it easier to open the door. Go try pushing on that door, 1 inch away from the hinges, and try opening the door. It's much, much harder, and you need a much, much bigger force to produce the same amount of rotation. And so our torque, intuitively, is going to be, well, here's its definition. What is torque? It is the cross product of how far away from the axis of rotation you're pushing times the force you're using. The further out from the axis of rotation you're pushing, the bigger the torque, the more you're going to get the door rotating. Or the bigger force you apply, the bigger the torque, the more you're going to get it rotating.
Okay.
Now keep in mind, it's actually a vector. So let's say that here's the hinges looking at a door from a bird's eye view. Here's my door, draw it out as an actual door. There's the door. I happen to, at this point R, so my R vector is pointing to where I'm pushing on the door, apply a force in that direction. So I'm pushing on some weird angle to open up the door.
Okay.
What is the torque that I produce?
It's a cross product of this.
It's going to be the cross product of those two. Now think about as a vector, remember, how do you take your cross product?
It's,
Point in the direction of R,
uh-huh.
point your next one in the direction of your second vector, F, and wherever your thumb's pointing gives you your torque. So in our case, the torque is coming out of the door
Weird.
board. This is why it's so unintuitive. The direction of your torque is going to be a bit confusing at first. Same with the direction of your linear momentum. It's kind of like going back to, remember when we talked about our omega vector?
Yeah.
What was our omega vector? If I've got a wheel right here in the board, and I've got it spinning this way, with some angular speed omega, what is my omega vector?
It points out.
It's the one pointing directly out if it's spinning counterclockwise.
Oh, yeah, right.
And it's the one pointing in if it's spinning if it's spinning clockwise. In clockwise, out counterclockwise. So you rotate your hand whichever way omega's going, and whichever way your thumb's pointing, that's the direction of omega. So now, it's very useful, well, it's going to be useful a bunch of the times, to actually think about your omega vector, your angular acceleration vector, your torque vector, and then your moment, or your angular momentum vector. So they are vectors, and that's what the vectors are. Initially, we're going to focus just on the magnitude of the vector. So the magnitude of the vector is like how hard I'm rotating the door. So what is the magnitude of R cross F?
R times F? The magnitude.
R times F times the sine of the angle between them.
Yep.
Now intuitively, if I were pushing on the door like this with the force right there, You might say to yourself, well, really, that's kind of like applying a force like this F right here. Because that portion of my force isn't going into rotating the door.
Yeah.
Yeah.
Right? If I were to come right here on the door and apply a force perfectly that way,
It would do
how much does that rotate the door? None.
Right.
So it's like the amount that's pushing perpendicular to it is all that matters. And so we memorized way back when we were first talking about cross products, the cross product, its magnitude is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them.
Yeah. Okay.
So notice that this vector is the same as this one, right?
Yeah.
Which is F sine of theta.
Yeah.
You see it? So it's giving me the direction that way.
Isn't that cosine?
No.
Oh yeah, that's fine. Okay.
Okay, good. Think about it when I was pushing directly this way. So my vector, my r is that way, my force is that way. What's the angle between them?
0 or
180. What's the sine of 180?
0.
0. And so the torque we're producing in that case is 0. And so to maximize your torque, you want the angle between your force and your r to be 90 degrees or minus 90, whatever, if you're trying to create a torque the opposite direction,
That makes sense. Okay.
to get the most rotation out of the door.
Okay.
So connecting it with the intuition, that's what torque is. And you're very familiar with torque, you use it all the time, right? You're loosening some sort of bolt, it's not working for you, you go and you get some bar and you stick it on your wrench so that you have more leverage and you can turn the bolt or whatever.
Yeah.
You're increasing the torque, that's all you're doing.
Right.
You're not suddenly getting more ripped and applying a bigger force.
Yeah.
You're just
Yeah.
increasing the radius to produce more torque so that you can get the bolt to spin. Okay, now I want to connect it to this relationship. So I want you to be able to think about torque this way,
Okay.
as moment of inertia times alpha.
Okay.
So that's what we're going to derive next. So force is equal to mass times acceleration. Good old Newton. The force tangent meaning it's perpendicular to your radius vector, that's what we're going to call your tangential force, is just going to be your mass times your tangential acceleration.
Right.
With me so far?
Are those vectors?
You can do it as a vector, but we could just talk about the magnitude, because this is just a magnitude relationship.
Okay.
Okay. Where were we? So your tangential force, mass times your tangential acceleration. Your tangential acceleration, remember, how are those related? It's the same thing as alpha times r. So your tangential acceleration, same thing as alpha times r. That's the only substitution I did from here to here. Okay, so now multiply both sides by r and we get this.
Okay.
What is mr squared? That's the moment of inertia for a point particle.
Yep.
So that gives us that relationship. So torque, you can think about it as the tangential force times r. Remember, tangential force would just be F times sine of theta. Combine those two together, that gives you F tangent. F tangent in this picture is this one right here.
Right.
Okay, so F tangent times r is one way to get your torque. That's the relationship we showed right here. Or the other way to get your torque is your moment of inertia times your angular acceleration, which is what we're showing right there. Good so far?
Yeah.
Okay, so before we move forward, let's just do some examples.
Right.
All right, so our first example, what's going on here? There's some bolt, some plumber's trying to take off. He puts a wrench on there. He has his wrench, he puts a pipe around his wrench. His wrench is attached, they're at some angle theta. His wrench makes the whole thing, I think, 1 meter long. I think it's 1 meter, doesn't really matter what it is. I'll double check in the book. And at the end of his pipe, he now applies a downward force, directly downward force, F. We know that F is equal to 900 newtons. And we know that the angle that this is at, theta, is equal to 19 degrees. We're wondering what's the torque he's now applying to that bolt right there.
A lot of torque.
Well, we'll calculate the torque.
Uh-huh.
Good so far?
Yeah, it's
Now, how do we calculate torque? We can think about torque as F tangent times R.
Okay.
So what's his tangential force?
It's
His
9.
force perpendicular to R.
Nine.
So let's put the F over here. We need to come make this triangle.
Oh, okay.
And we need to break it up into two triangles. This force, we need to break it up into the force this way and the force that way. It's those two forces. So there's F tan. It's this side. This angle right here is still going to be theta. And so what is F tangent?
How do we know that angles? Yeah.
What would be the best way for you to see this?
Is that just geometry or what?
Yeah, it's going to fall out from geometry.
Is it one of those circle theorems or?
No, it's just that's a right angle. Okay, let's scribble out the geometry really quick. So I'm making a right triangle. That's intended to be right, so this is a right angle with a line straight down. The triangle we create over here is similar to the whole triangle. How do I know that? This is a right angle, so that angle is the same big as that angle. And this angle is the same for both of them. So the remaining angles have to be the same.
Oh.
There's a geometric way to see it, where you can just think, if I've got my hands perpendicular to each other, the more I raise my hand, that's not really a good way to see it, I don't know if you can really see it. If I raise my hand, this one some degree, if I raise that one 20 degrees, then I've tipped this one 20 degrees.
Everyone here?
Everyone's here, thanks. So there's another way to try and get the intuition.
All right.
But either way, there it is. Let me just draw it bigger so that we can see stuff a little bit better. So we got our force here. Doesn't matter how big we draw it. There's F. We draw this one. And now that's like that. Here's F tangent. And this is going to be the same angle as that. With me so far?
Yeah.
So what is F tangent then?
That is cosine of theta times F.
Perfect. So F tangent is equal to F times cosine of theta. Right?
Yeah.
Now, here's why I don't like blindly memorizing formulas. You might say, wait, F R times sine of theta.
Yeah.
Well, that's true when you use the angle between them. I didn't choose to use this angle. I chose to use this angle.
Right.
So if I call this angle right here alpha, then it will also be that F tangent is equal to F times sine of alpha. And that will be true. Because if this is 19 degrees, then this one's going to be 71.
Yeah.
And the cosine of and the sine of 71 is the same thing as the cosine of 19.
Yeah. Weird.
Not really. Your y coordinate, 19 degrees this way, is the same as your x coordinate, 19 degrees this way.
Oh.
So, very natural symmetry.
Yeah.
So, it still works out. I just chose not to calculate that way. Because I didn't want to work with alpha. I wanted to work with whatever this theta was. Anyways, so this is going to be equal to F is 900 times cosine of 19 degrees times R is, let's actually check now, 0.8 meters. Okay. So 0.8 meters. And we throw that into our calculator. Where did I put my backpack? And so we get 900 times the cosine of 19 times 0.8 equals 681 if we have 3 significant figures. I think we only have 2 significant figures on this problem. I think everything's given to 2 significant figures. So that's going to be 680 times 0.8. And so that's all going to be 680.
80 what?
Okay, 80 what? Here's the question. Notice how we got this. We did a force times a distance. So we did Newton meters.
Which sounds like joules.
Which sounds like joules, but this is not an energy. So unfortunately, sometimes the same units show up in 2 different ways. This is the magnitude of a vector. This is not energy. So you can do Newton meters, do not do joules.
Why is
Joules means energy.
Why is not energy?
Because torque's not energy.
Kind of makes a lot of sense that torque would be an I don't know, I guess not.
Why does it have the same units as energy? Well, when we come and we calculate energy, you notice that we're just going to be taking a torque and multiplying it by a radial displacement. Radians are a dimensionless unit, so it needs to already have the same dimensions as work does.
Oh, I see.
So I would say that's pretty much all I can read into that on the fly. I don't know, maybe there's some deep relationship I don't have a connection with. But Newton meters, that's what it is.
Okay.
Or kilogram meter squared per second squared if you want. But not joules. Never joules. Okay. Any questions on that problem? Well, forever hold your peace. Okay, next one. So how does this problem work? We've got some wheel rotating right here. We're applying a force F to get the spin. It's mounted in place, so it's not going to roll. So it's up in the air some. Alright? Here it is spinning. We're applying some force F. The force F we're applying on it is 9 newtons. The radius of this thing is 6 centimeters. And it has a mass of 50 kilograms. It's a solid cylinder, so its moment of inertia is 1/2 mr squared. Our job is to find alpha and then the tangential acceleration of this rope that I'm uncoiling off of it. So I'm uncoiling a rope off of it. The rope is massless for our purposes by applying some force, 9 newtons. How fast is that rope accelerating as I'm applying that force? So like if we were to look at an atom on the rope right there, how fast is it accelerating that way? That's what that is. And angular acceleration is how fast this thing is speeding up as I'm uncoiling it faster and faster.
Wouldn't they be the same?
No, they're going to be related. They're going to be related by this relationship. This is meters per second squared. This is radians per second squared.
Yeah, that makes sense.
Okay, so let's go ahead and start working away at this problem. So first off, what is the torque that I'm applying right there? What is my torque?
It's 1/2.
It's just F times R is one way to get the torque, right?
Right.
Because it's already completely perpendicular, so it's already our tangential force.
Right.
So one way I can get that is F times R. But I can also get it as a moment of inertia times alpha.
But we don't know alpha.
No, we don't know alpha, but I need an equation to get alpha.
Oh.
So F times R is also equal to our moment of inertia, which we know.
Oh, that's cool.
I'll write out the moment of inertia. You okay with me writing it out?
Yeah.
Did we use a little m or a big M?
Little.
Should have used a big M, but I wrote a little m. 1/2 mr squared, our moment of inertia, times alpha. You with me so far?
Yeah.
Okay, that's our torque.
Now just solve for alpha. You know.
We have everything else, right?
Our acceleration tangential is just alpha. It's just F, right?
Yeah, okay, so we have all these other quantities. So, we can divide an r out from both sides. And so I'm going to get alpha is equal to, move the 2 over here, that's going to be 2f, divided by m, and divide by another r. Did I do everything right?
Yeah.
So if we plug all that in, 2 times our force was 9 newtons, divided by, our mass was 50 kilograms, times our radius was 6 centimeters. And it comes out to exactly 6. So that's going to be 6 radians per second squared.
That should be 6.0, right?
6.0. Good point. 2 significant figures we have for everything. Okay, so now what is our acceleration? Well, we have this relationship for our acceleration. It's just alpha times r. What's our r? 0.06. So 0.06 times 6 is just going to be 0.36. And that's going to be meters per second squared. And that is our tangential one if you want to keep track of that.
I thought F was tangential acceleration in our equation.
That was how fast that thing is accelerating, that point mass. So it's how fast a mass right on the surface of your wheel is accelerating.
Is that not the same thing as tangential?
Yeah.
We have different answers. Oh.
No, we have two answers. Alpha and A.
My question is F in that drawing, is that not the same thing as our tangential acceleration?
Yes, it is.
But F is 9.0 and our tangential acceleration is 0.36 meters per second squared. Oh, I guess F is in newtons.
F is our force, and it's a tangential force.
Yeah.
It's completely different from our tangential acceleration.
Okay.
Okay. Any other questions on that one before we move on to the next example? Okay. Next example, what we have is we've got some big drum, once again, with some radius r and some mass big M. We've got a rope tied around it, attached to some other mass, little m. We know that the moment of inertia, that's going to be a solid cylinder, is 1/2 mr squared. And I think that's everything we have. And we're looking for how this block is accelerating downwards, and then for the tension. So this is some sort of coil with wire on it, and it's unwinding as this block is falling to the ground. We want to find out how fast is this block accelerating downwards, and then what is the force of tension inside the rope. Understand the physical scenario? Okay, so let's look at the forces, and then we'll look at the torques. So first off, what are the forces in play? Like think about the free body diagram for this mass here.
There's gravity.
There's gravity pulling it, we'll call it down the positive direction since that's the way it's moving.
Okay.
And then there's tension pulling it up. So I know that for this object, its mass times its acceleration is equal to mg pulling it down minus t pulling it up.
Yep.
Good so far? Now, let's look at the torque of the system. Torque only applies to this thing. This is the thing spinning, right? As it's uncoiling.
Yeah.
I don't know if I'll make it some constant. It could be speeding up. It's going to be speeding up as it goes. So spinning around, however it's spinning around. Okay, what's causing it to spin? What's the force providing all our torque?
It's the
Gravity.
No, it's the tension. If I cut the rope, nothing's providing the torque anymore.
Right.
It's not gravity pulling on this. I mean, ultimately, as a side effect it is. But it's the tension here that is causing it to spin.
Right. And the tension is caused by gravity, though.
Ultimately, gravity is causing the tension.
Right.
But it's the tension that is causing this to turn.
Yeah.
It's not the full mg.
Okay.
Good?
Do we lose
Because the torque is canceling out some of that.
Oh, right. Okay.
If tension was exactly equal to mg, this object wouldn't be moving.
Right.
So it's the tension providing our torque. So one way to get this torque here, it's going to be it's perfectly perpendicular to the radius. So one way to get that torque is we know that it's tension times r, because the sine of the angle between them is 1. What's the other way we can get that torque?
The moment of inertia.
Times
Times your angular acceleration.
times your angular acceleration. So this is also equal to your moment of inertia times your angular acceleration. Good? Okay, I'm going to solve this one for t really quick.
Okay.
So that is going to be t is equal to, I'm moving this to this side and the ma to that side. So it's equal to mg minus ma. And now down here, so those two equations were both the same equation. Now down here, t times r is equal to, moment of inertia is going to be 1/2 mr squared, since we're a solid cylinder. And now alpha, notice that how fast this object is accelerating downwards is exactly the same fast as this object, the point on the surface of the circle is accelerating around.
Okay.
Those are the same acceleration.
Yeah.
It's a tangential acceleration. So alpha is the same thing as my acceleration divided by r.
Okay.
So I'm going to write this as a over r instead of alpha. With me? Divide both sides by r, so I get, sorry, big R. Divide both sides by r, so this r cancels out with one of these r's, still leaving one. This other r cancels with that r. So all of our r's are gone. And so I get tension is equal to what? 1/2 ma, big M. Okay, so I got tension is equal to this, tension is equal to this. Solve for A. Substitute this into there, solve for A. So, plugging that in, I get 1/2 ma is equal to mg minus ma. Move this to the other side. So add ma to both. Are you good up to here?
Yeah.
Okay, add ma to both sides. How many? Sorry, that's a big M and a big M. Oh wait. Ooh, be careful. No, it's not necessarily. Make sure I do this all correctly. We had 1/2 m big ma is equal to little mg minus little ma. Right?
Yes.
Okay. Can't mess up those masses. Now I need to solve for my A here. So I'm going to move this over to this side.
Okay.
And factor out the A's. So I get A times 1/2 big M plus little m is equal to mg. I move that over and factor out my A's. Divide both sides, and I'm going to get A is equal to mg over, rather than writing that as 1/2 m, I'm going to write that as big M over 2 plus little m. You with me?
Yeah.
And then the way the author had it is he divides everything now by little m. So divide that by little m, that by little m, that by little m. And we're going to get g over big M over 2 little m plus 1. And that's the answer he has. Pretty sure. Let's double check. Worth not making a mistake.
Did he give values for that, or is it just?
No, it's just completely in symbols.
Right.
So A, he got G over 1 plus big M over 2 little m. Okay, so he just wrote 1 plus big M over 2 little m. That's the only difference. Let's put the 1 here. Just be consistent. Good?
Mm-hmm.
So now we need to find the tension. Well, substitute A in right here and find the tension. So tension now is equal to, I was right as M over 2 for those two times A. What was A? G over 1 plus big M over 2 little m. Now, I have no clue how he chose to write it. He wrote it as an M, little m, G in the top. Okay. So let me rewrite this and then we'll write it his way. So in our top, this goes to the numerator. In the top, I have big M, G over 2, all over 1 plus big M over 2 little m. T equal to. Good? Now he just has an mg, a little mg in the top here. So to get that, I need to multiply this by little m, 2 little m over big M. So I need to do that to this term, and I need to do that to each of these terms, so I'm not changing anything. And times this whole thing by 2m over big M. Just try and get the same way the author has it. Okay, so now this is going to be equal to, we're going to get tension is equal to, the 2's go out, the m cancel with the m, leaving me gm, or mg in the top. For this one, it's just going to be 2 little m over big M. I'm going to write that on this side. Because now when I multiply that to that, it's going to be 1. So we get 1 plus. Okay, so there's that one. And here's the other one. You double check with the author. mg over 1 plus 2 little m over big M. Yeah. Okay, so there we go. Calculate the tension, calculate the acceleration. Good? Woohoo. Alright, so that's introducing torque. Now let's talk about finding the kinetic energy of a rigid body. A rigid body that both has linear motion and also has angular motion. So I've got some random rigid body here. I've got some random rigid body here that I take, and it's been thrown through the air.
Okay.
If you follow its center of mass, here's the path its center of mass is taking through the air. But while it's going through the air, it's also just spinning however it's spinning. And so our job now is to calculate the kinetic energy of an object that both has linear motion and angular motion. Now, what do we want the answer here to be? If I asked you what was the kinetic energy of this object without even doing the derivation, what would you say?
It's kind of like both of them add together.
Yeah, you would say it's probably both of them added together. So you would have guessed something like 1/2, the mass of the whole object, we'll use big M for its entire mass, 1/2 m, the velocity of the center of mass, squared, plus 1/2 I, its moment of inertia, whatever that is, times its angular speed squared. And that probably would have been your guess. That's a very good guess. And we're going to prove that that guess is in fact correct.
Sweet.
Good?
Why can't we just divide it like that?
The definition of kinetic energy for a point mass is K is equal to 1/2 mv squared.
Right.
That's its definition. We proved that for a rigid body, this is the case when it just has linear motion. And we proved for a rigid body that this is the case when it just has angular motion. You can't define this as the kinetic energy of a rigid body. It's all going to fall out from this one definition.
Oh, okay.
So now we're going to prove that you can just sum it the way you know and love, and it works.
Okay.
So this all comes from just this definition for a point like mass. Everything else follows from that.
Oh.
So we don't have to have a new definition for kinetic energy for a rigid body flying through space that's also rotating. Okay. So how are we going to do this? Well, first off, here's my picture. Right here. Here's our object moving. The velocity of the center of mass is just going along whatever the arc is that the object's following. But when we talk about some infinitesimal part of this thing, some mass, m sub I here, some mass, m sub I here, what's the velocity of that thing? Well, it's going to be in some weird direction.
Right.
Because it's going to have some velocity that way because that's how the whole object's moving, but it's also turning, and so maybe its velocity is pointing up some like that. And so we're going to calculate the kinetic energy of this rigid body by calculating the kinetic energy of all these little m sub i's all over the object and adding them all up. That gives us the total kinetic energy. With me so far? Okay. First thing I'm going to do is I'm going to create a notion of v sub I prime. This is going to be the velocity that the object has relative to its center of mass. Imagine I hooked you right there on the center of the object and threw you through the air. Relative to you, what is this point mass doing?
Rotating around.
It's just going to be rotating around you. Right?
Yeah.
So, v sub I prime is going to be the velocity of the object relative to you as a point mass there. I'm standing back here watching the whole thing. So v sub I here is going to be its velocity relative to me.
Yes.
You're at the center of mass. Now how do you get from one velocity to the next? The velocity of the whole thing is equal to the velocity of the center of mass plus the velocity relative to the center of mass.
Okay.
So I'm defining it this way. What's v sub I prime? It's v sub I minus the velocity of the center of mass. But what that gives me is this equation. This is probably the more intuitive way to think about it, which is its velocity relative to me is equal to your velocity relative to me plus its velocity relative to you.
Right.
Does that make perfect intuitive sense? Or should we scribble out an example? Let's go back to our train made out of glass. You are bound on the train so you can't move. You're stuck there. Can't move. And so the velocity of the center of mass is just whatever your velocity is in this picture.
Yeah.
Now let's say that some object in the train relative to you is just falling straight down. So here's v sub I prime. Relative to you is just falling straight down. What is it doing relative to me? We'll call that v sub I.
Moving diagonal.
It's got this v sub the center of mass plus v sub I prime.
Yeah. Yeah.
It's going to be the sum of those two things. Sorry, everything here is vectors.
Yeah.
Just being a bit lazy. And it's going to look like something like this. Is what the velocity is going to look like relative to me.
Yeah.
So exact same thinking going on here. So v sub I, that's the velocity for me. Velocity of the center of mass, that's how you're moving relative to me. And then v sub I prime is how it's moving relative to you.
Okay.
Good so far? Okay. So now, the kinetic energy is equal to the sum of 1/2 m sub I times v sub I squared for all the little particles. That's what the kinetic energy is from my reference frame watching this object move through the air. Just by definition. Okay. Now, go back to our vector notation. What is a vector dotted with itself? If I have A dot product A, what does that give me? It just gives me the magnitude squared. Do you remember that?
Yeah.
Do we need to see that real quick?
No, that makes sense.
Okay, makes sense. Okay, so I'm going to be using that fact. It makes so I can do a clever substitution. I can rewrite v sub I squared as v sub I dotted with v sub I looking at the vectors.
Oh, that's smart.
So, now what is v sub I as a vector? It's this whole thing.
Yeah.
So I can replace that v sub I squared with v sub I dotted with v sub I, and now this is not times, that's dot product, as in a vector dot product. Good so far? So kinetic energy is equal to the sum of 1/2 the mass times the dot product of these two velocities. Okay, you may not remember this, but we proved all the way back first lecture, or whichever one we dealt with vectors, maybe second lecture, that dot product is distributive.
Yeah.
Over addition. And so I can break this up and I can multiply each one to each one. So V center of mass times V center of mass, or V center of mass dotted with V center of mass gives me V center of mass squared. I have V center of mass dotted with V sub I and V sub I dotted with V center of mass for two of them. So I have two of those. Two V sub I dotted with V center of mass. And then V sub I dotted with V sub I, once again, is just going to be, or V sub I prime dotted with V sub I prime is just going to be V sub I prime squared. And I just broke the sum up into three separate sums.
Yeah.
So we have 1/2 m sub I times VCM squared plus 1/2 m sub I times the 2 we got from that, and then 1/2 m sub I times those two together. Just breaking each one up into its own sum. Sorry, I know that's dense notation, but I think it's fairly straightforward what's happening.
Yeah.
Okay, now in these sums, let's look at the first sum. Does the velocity of the center of mass change as I go from point particle to point particle? No, so it's a constant, so we can factor that out.
Okay.
Once again, over here, 2 is a constant, so we can pull that out to cancel out with the 1/2. And the velocity of the center of mass is once again a constant, so we can pull that out front. And understand, this is still dot product. We're doing m times all those vectors, adding them all up, result of vector, take the dot product. And then finally, over here, V sub I prime, remember, how was this object moving relative to you? It's just going in a circle. And so that is its rotational velocity. And so that is going to be the same thing as omega times r. So I'm replacing your V sub I prime with an omega times r, squared, squared. Good? Okay. Now, once again, go through this whole line again. Notice we factored everything out of here except for the masses.
Yeah.
So now this is just the sum of all the masses. When you sum up all the masses, what do you get?
Big mass.
The total mass. So that's 1/2 the mass of the entire object times the velocity of the center of mass squared. Okay, we got that term to show up. Surprise. Now I'm writing the second term next. Notice what we have here. We have 1/2 the mass times, that should be r sub I, because the radius changes from point to point. We have 1/2 the mass times the radius squared, which is
The moment of inertia.
moment of inertia, and then the omega is the same for the entire object, so you can factor all that out.
Right.
So that gives us 1/2 moment of inertia times omega squared.
Okay.
Okay, and now all we're left with is this weird middle term. We have the velocity of center of mass dotted with the sum of all the masses times their velocity in your reference frame. Now, I'm going to try and make this first appeal to your intuition, why this sum right here is 0, and then I'll actually prove that it's 0, but first try and connect the intuition. This is the sum of all the masses times their velocities. The velocity of the center of mass in some reference frame, velocity of the center of mass in some reference frame, is m1 times v1 plus m2 times v2, m2 times v2 plus ... all over m1 plus m2 plus ...
Yeah.
That gives you the velocity of the center of mass in whatever reference frame you're talking about. If these velocities are all our prime velocities, what is the reference frame we're talking about?
Ours.
Your reference frame, which is the center of mass. What is the velocity of the center of mass in the center of mass's reference frame? 0. And so this sum, the numerator there is going to be 0. Because the mass obviously is at 0. So the numerator has to be 0, which is exactly what this sum is.
Okay.
There's the intuition. Now I'm just going to go through the algebra. But that's all it's going to say. So let's see what I said here. Observe the velocity of the center of mass, exactly what we said. The sum of all the masses down here is what we mean by big M. So I'll move big M up over here, and that's how we get this. Big M times the velocity of the center of mass is equal to the sum of m1 times v1 prime plus m2 times v2 prime. Those are all the primes. That was I was just saying that's the case in general. So now down here, taking this sum, proving that is 0, I need to prove that the sum of all the m sub I times v sub I primes, when you take that sum, you get 0. Now what is v sub I prime? We can rewrite it as v sub I minus v sub m. So v sub I prime, I'm just rewriting that as v sub I minus v sub m. And now I'm going to split the sum into this times this over and over again, minus this times this over and over again. So just split it into two sums. Now what is this sum over and over again?
That is the.
We already showed that that sum just gives you the mass times the velocity of the center of mass. Velocity of the center of mass is a constant here, so I can factor that out, and you're just now adding up all the masses, which gives you a big M. And so you're going to be left with mass times the velocity of the center of mass minus mass times the velocity of the center of mass, which gives you 0. So there's algebraically proving it, there's the intuition for proving it. With both those, hopefully it makes sense. So that term goes to 0. And anything dotted with 0, still 0, and so only those two terms remain our final answer. Da 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 da.
Oh, easy. Cool.
Good?
Yeah.
Okay, more examples. Now we know how to deal with energies. So probably have to use energies for this next example. This was primitive yo-yo, I believe. So what's going on here? We're taking just some solid cylinder, we're wrapping a string around it a bunch of times, and we grab that string and let go. It's going to fall.
Okay.
Called primitive yo-yo. So that's what's happening here. Our primitive yo-yo has a radius r, which starts right there when we're holding that string, and we let it go, and it's going to fall some distance h.
Oh, you're trying to figure out how it rotates.
And by the time it falls h, the question is, how fast is it moving? What's its velocity?
It's linear velocity or it's angular velocity?
The velocity of the center of mass moving downwards.
So it's linear velocity.
Yeah.
Okay.
With me so far what the question is? Because think about what makes it fall faster. So in one case, I could hold the string and let it fall. Or in another case, I could not hold the string and let it fall. Which one falls faster?
The one where you're not holding the string.
The one where you're not holding the string.
Is that just because of
Because the tension's bringing it up.
there's energy going into.
If you want to think about it in terms of energy, some of the energy went into actually spinning it, and so it can't all go into kinetic energy.
Okay.
If you want to think about it as forces, there's a tension pulling up on it. And so it's not accelerating downwards at the same rate. So however you want to think about it. So the question is, how fast does this fall?
Okay.
You've done falling objects, and just a falling object, that's trivial for you now.
Yeah.
But now a falling object that's spinning as it goes, that's a bit more tricky. Now always and forever with our energy, what's the equation we use? Your initial potential energy plus your initial kinetic energy plus the work that goes into the system is equal to your final potential energy plus your final kinetic energy. Right? Told you, you're going to use it 1 trillion times.
Yeah.
Never goes away. Alright, what is our initial potential energy when the object's up here?
MGH.
MGH. We're using a big M. Okay. So sorry, my big M's are awful. mgh. What's our initial kinetic energy the instant we let go?
0.
0. What's the work we're doing on the system?
0.
0. Okay. What's our final kinetic energy?
It's 0.
It's gonna be whatever it is.
It's going to be 0. We're defining this to be our 0 potential energy. You can define 0 potential energy wherever you want. It doesn't change anything.
Yeah.
Does that make sense to you that it doesn't matter where we define our potential energy?
Yeah.
I don't trust you. I'm going to say that this right here, we're going to call 10,000 meters in the air.
Okay.
So now this is going to be 10,000 inch meters in the air. Okay, so now what's our potential energy here? It's mg times 10,000 plus h. Okay.
Okay.
And this is equal to, our final potential energy is going to be mg times 10,000. Well, I should have done that, now I'm running out of space. Plus our kinetic energy.
The 10,000s cancel out. Basically.
Yeah, it's all going to cancel out, which is why it doesn't matter what you call 0. All that matters is the difference between the two. All that's going to matter is the h.
Yeah.
So, maybe I already see that, so I can have my space back. Okay, so we got mgh is equal to final potential energy, 0. What's our final kinetic energy?
That is what we're trying to solve.
Come on. What is it? Here's what we know. We know h, we know r, we know m, and we know that I is equal to that.
It's the sum. So it's your linear kinetic energy plus your angular one. So it's 1/2 mv
Squared.
mass.
The center of mass squared, good.
Plus 1/2 your moment of inertia times your angular speed squared.
All right, moment of inertia. Sorry, that one's hard to spell. And then times what?
Your angular speed squared.
No, just square.
We don't really have a. I mean, we could put an omega squared there, but what are we gonna do with that omega squared?
It's a great question.
Sugar.
Rewrite it as.
We'll write it as omega squared for now.
Velocity.
How? It's not just equal to velocity. This is radians per second. Velocity is.
Oh.
It's velocity squared over r squared.
Oh. It's you times it by r over v.
It's the velocity of our center of mass squared divided by r squared if we do the substitution.
Yeah.
What is just omega by itself equal to? It's equal to the velocity of your center of mass over r.
Yeah.
Why is omega equal to the velocity of our center of mass over r? Because how fast this thing is uncoiling is the exact same speed that it's going down. If I went down a meter, I had to uncoil a meter.
Oh yeah.
That's why they're the same. Good?
Yeah.
Okay, so making that substitution, then this is just going to be velocity of the center of mass squared over r squared. Good?
Okay.
That's our omega squared.
We're trying to solve for velocity center of mass.
Yeah. Now, what a beautiful equation. R squared, how annoying, get out of there. M's, how annoying, get out of there. And what are we left with?
GH is equal to
1/2
CF squared plus
Oh,
plus
and
one
the
quarter.
And the
Yeah, BCF. Oh, so that goes to 3/4 BCF squared. GH equals 3/4 BCF squared. So BCF squared is with 3 or 4/3 GH. That's cool. Square
There we
root
go.
of pi, we squared it. Okay.
Now look at how crazy this is. The mass didn't come into the picture, and the radius didn't come into the picture. All that mattered was the actual shape of the object, how high it was, and then the pull of gravity. So what's crazy about that is only the geometry of the thing
Where did the geometry come
affected how it fell as opposed to the mass. It gave us this 1/2. The fact that it was a solid cylinder introduced that 1/2
with the moment of inertia?
with the moment of inertia. It just affected that coefficient.
Right.
If this were instead
hollow.
a hollow one, then that would get rid of that 1/2 there.
Okay. That's cool.
So if I got rid of that 1/2 there, what would that have done to the problem? Would it have fallen quicker or slower?
Got faster. Because if you would have got faster, because you would have got rid of the quarter. Right?
It'd fall quicker.
Let's just use our intuition first. So if instead of having it a solid cylinder, I instead make it a hollow cylinder. So all the mass is on the outside. I make the moment of inertia bigger. Is that going to eat up more of my energy or less of my energy?
What?
It's gonna eat up.
Because it has to rotate as many times as it has to rotate to uncoil as far as it uncoils in age.
And they have the same mass.
So, same mass, but mass didn't even matter in this. No, this time we quadrupled the mass. It's not changing anything.
Yeah, it won't change it.
So just changing that geometry. Now, if I made it a hollow shell, change that geometry, all the mass is now on the exterior. The moment of inertia is bigger, so it's harder to spin, so it should have a smaller velocity. Let's just redo it with that. If we got rid of our 1/2 here, what happens? This becomes 1/2, this becomes 1, that becomes a 1. 1 is smaller than 4/3, so velocity went down.
Yeah, you're right.
Good?
Yep.
Okay. Nice over.
Okay. Let's do exercise. Well, we're kind of primed for exercise 5. But exercise 6 is really important. Let's do exercise 5. Exercise 5 now is I've got some ramp here. And on that ramp, I'm going to put a bunch of different objects. One of them is going to be a solid sphere. One of them is going to be a hollow sphere. One of them is going to be a solid cylinder laying on its side. One of them is going to be a hollow cylinder laying on its side. So that one's solid, that one's hollow. And then finally we're going to take a disc, like a penny.
Isn't that just the solid cylinder? This is the other one.
Yep. So you already got one of the tricks. And a penny. I put them all on this ramp. They all have identical weights, and they all have made of identical materials. And I roll them down the ramp. Which one gets to the bottom first?
I want to say
Circle.
the solid sphere.
Solid sphere.
Solid sphere?
I need to remind myself of the moment of inertia for them though.
And the answer is yes, solid sphere. So a solid sphere was 2/5.
Kind of makes sense because like most of the mass is going to be more constant.
Right, you're just thinking about which one has most of the mass there. And it turns out it's all just related to the moment of inertia the same way that this problem was. Because the height's going to be the same for all of them, and the g's going to be the same for all of them.
Right.
And so it's simply a question of geometry. You can make a solid sphere out of plastic, ignoring air resistance. Someone can make a completely solid cylinder out of a dense metal, as long as it's not like breaking anything. And yours would still win to the bottom. Do it in a vacuum, go do it on the moon. You got a styrofoam solid sphere, and they've got, a metal solid cylinder. Race them down the ramp, yours is going to win.
That's kind of cool.
Yeah, it's crazy. It just depends upon the geometry.
That's great.
How the mass is distributed, not what the total mass actually is.
Right.
Okay, so that was problem 5. Okay, problem 6 now is making reference to our same yo-yo that we had before. So back to our primitive yo-yo. This is on a string, it's falling to the ground. So it's got right here pulling down on it, mg. And pulling up on it here in the string, we have some force of tension T.
Wait, what is the difference between a primitive yo-yo and an actual yo-yo?
A primitive yo-yo means that there's nothing special to it. You're just taking a string around some solid cylinder, holding it and watching it fall.
Why do we call it primitive?
Because you can't make it any simpler.
Do we have like an actual yo-yo?
No. It's going to be similar to an actual yo-yo. We're just saying it's an idealized situation, so you don't have to worry about any of the other things. Okay. What are we looking for? This time we are looking for the acceleration of the center of the mass, how it's accelerating downwards, and this time we're looking for the tension in the rope. Good? So with this problem, we're going to have to look at the forces and look at the torques. So let's start by looking at the forces. I'll call downwards a positive direction since that's the way it's moving.
Okay.
So my mass times my acceleration downwards, which is the acceleration of the center of mass that I think, is equal to what?
Force.
What are the forces acting on the sink?
Gravity.
Gravity down
And the tension up.
and the tension up.
Yes.
I'm calling gravity positive. I'm calling down positive, so mg is going to be positive, and it's going to be minus t. That's the forces. Now let's look at the torques. Once again, this is a solid cylinder, so it's still the case that moment of inertia is 1/2 mr squared. The torques on this, what's the torque I have? The only thing causing it to spin is the tension, right? Its weight is not causing it to spin. The tension's causing it to spin. Okay, so what is the torque from the tension?
It's TR.
TR. And that is also equal to, what's the other way we get the moment of inertia? What's the other way we get the torque?
Inertia times angular acceleration.
Perfect, moment of inertia, 1/2 mr squared for this one.
And then angular acceleration, which is v over r.
A over r.
Oh, okay.
Because it's the angular acceleration, not the linear speed, or not the angular speed. Okay, once again, two equations, two unknowns. First off, let's notice some things. Divide both sides by r, that gets rid of one of those r, then that r cancels the other one. Okay, r's go out. So the radius of the sink, once again, doesn't matter. It's going to be the geometry that matters.
So the torque is equal to the tension, sorry.
So up here, let's rewrite both these equations. I'll do the top one first just so we have them in the same order. So I'm going to say tension is equal to mg minus m times the acceleration of center of mass. Moving the t over here and the ma over there. And now this one, solve for t, it's already solved for t. Is t is equal to 1/2 m ACM. Okay, set those equal to each other and I can solve for the acceleration of the center of mass. So I get 1/2, I'm going to write this one right there.
Yeah.
ACM is equal to mg times m ACM. And you move that to the other side and factor out the ACM. So I'm going to get ACM times, I'm going to write that as m over 2 plus little m is equal to big mg. Wait, why do I have little m's and big m's? There's just big M. There's just the mass of this sink. All our m's are the same.
This is center of mass. But yeah.
You go through the algebra between that step and that step.
From here to here, move this to the other side, so we plus m ACM, and then factor out the ACM.
Oh.
So 1/2 m ACM, and then m ACM. Those are both the same m's. So divide through by m, and then 1/2 plus 1 is equal to 3, times 3/2 is equal to g. Or ACM is equal to what?
2/3 g.
ACM is equal to 2/3 g. Notice that the acceleration of the center of mass would just be g if I cut the string.
Yeah.
So the tension has to be slowing it down, and what do you know? It is slowing it down.
Wait, so if this is purely dependent on geometry, does that mean that equation is true for every solid cylinder?
Ignoring air resistance, every solid cylinder where the mass is uniformly distributed.
So it doesn't matter what your mass or your radius is, or
None of that matters. It's crazy. It just matters what the shape is.
that's cool.
Okay, now let's find tension. Well, tension we can just get from this bottom one, plugging that in. So tension then is equal to 1/2 times 2/3 is 1/3 mg. And so the tension is canceling out 1/3 the weight, which makes sense because 1/3 the acceleration was being canceled out.
Right.
So nothing shocking there. Good? Okay. Finally, example 7. Example 7, this time we have a solid sphere rolling down a ramp. Now it's rolling down a ramp, so there has to be some force of friction causing it to roll. If I took a ball on a perfectly frictionless surface, perfectly frictionless ramp, and let it go, it wouldn't roll. It would just slide. You need friction to get it to roll.
So the kinetic force or the
It's going to be static
addition
friction.
of static, yeah.
Well, we're just going to call F sub S the whole thing of static friction.
Yeah.
So the constant times the normal force. We're not going to
I guess
overthink
it's
it.
all static because you're never sliding.
Right, because it's not skidding as it goes.
That makes sense.
It never breaks, yeah. Interesting thought.
Okay. Beta, I don't know why they chose to use beta, but beta is the angle it's rolling down at. R is the radius of our bowling ball. M is its mass, and we're assuming it's a solid sphere, so its moment of inertia is 2/5 mr squared. Good so far?
Mm-hmm.
Okay. Our job is to find how quickly it's accelerating down the ramp, and then what our force of static friction is. Good?
Mm-hmm.
Now let me just scribble out a free body diagram for this thing. So here's our ramp coming over. This right here is beta. We've got point right here. It's going to have, pulling it down is big mg, right? Come over here perpendicular to our ramp. And then we're also going to have this one. So if this, sorry, not sure how well you can see that. If that's mg, this right here is going to be our beta. This side over here is going to be cosine. Over here is our mg cosine of beta. We don't really care about that side, but just for completeness, what we care about is this side, which is mg sine of beta.
Yep.
Okay, upwards we got our normal force right here. And then right here we've got our force of static friction. This force has to be bigger than our force of static friction because the ball's moving downhill. So I'm going to call down the road or positive x direction, down the ramp. So let's look at our forces in the positive x direction, because in the y direction everything cancels out. So looking at forces in the x direction, what do we have? So my total mass times my acceleration of my center of mass has to be equal to my net forces in the x direction. I've got in the positive direction mg sine of beta, right? Mm-hmm. Minus what's opposing me?
Your
Friction,
force.
which is F sub S.
Yeah. I'm kind of like.
Yeah.
Okay.
Are we all here?
Yeah, I just reconnected.
No one in the hall? Okay, let's look at the torques in the scenario now. What is making the bowling ball spin?
The friction.
Friction, just friction, nothing else. So the torque better only be dependent upon friction or we done messed up.
Times radius, right? Friction
So,
times
perfect. So force of, one way to get the torque is F sub S times R, which will also be equal to,
Your angular
That's your torque.
moment of inertia times.
which will also be, remember, we have two equations for our torque, right? Both up here. This, one of the standard ways we get is F times R, where F is your tangential force. And then the other way we get it is I times alpha.
Yeah.
And so solving the torque these two different ways is going to give you the equation you want with your torque. And so Fr is equal to
Moment of inertia.
moment of inertia, in our case 2/5, not 1/2.
Angular acceleration.
Perfect. So 2/5 times m times r squared times our angular acceleration. How can I rewrite that?
V over R.
It's
A over R. Sorry.
A center of mass over r.
Sorry.
Why can I write it that way? The exact same amount that this ball moves down the hill is exactly how much is spun.
The distance you're saying.
Yeah.
Yeah.
So if we were to follow an atom on this bowling ball, however far it moved around the bowling ball is equivalent to how much the bowling ball moved down the ramp.
Yeah.
And so how it's accelerating around the bowling ball is equivalent to how the bowling ball is accelerating down the ramp.
Yeah. That makes sense.
Okay, so that's why we can make that substitution. The bowling ball is not slipping. If it was slipping, then that would no longer hold, and this is a whole mess of a problem.
Yeah.
Yeah, how would you do that?
Not easily, not tough. Any other hard questions? Okay, so once again, notice divide both sides by r, and then r and r go out again. So all the r's are gone. Woohoo.
That's right.
Okay, so now we have,
F equal to.
so let me rewrite both these equations, sorry. So rewriting this one first for f of s. I'm going to move the f of s over here and the MAC over there. So I got f sub s is equal to
mg sine
mg sine of beta
minus
minus ma center of mass. And then from this equation, I have f sub s is equal to, we still have our 2/5 m
and then
a center of mass. Okay, to get the a center of mass, we just set these both equal to each other.
To get your A.
To get your a, so I'm going to write this as, okay, I won't do it all, no, sorry. I have 2/5 ma center of mass is equal to this sink.
Yep.
I'm going to move this over on the other side. So I'm going to say plus ma center of mass, you with me so far? Is equal to mg sine of beta. Now what do we notice?
That the
2/5.
oh factor, right? No.
Divide by m.
It's 2.
Divide by m. Divide both sides by big M, all the m's go out.
Well,
Okay, with me so far?
Mm-hmm.
And I have 2/5 ACM and 1 ACM for a total of 7/5.
what?
2/5 plus 1, or 2/5 plus 5/5 is 7/5 is equal to g sine of beta.
Oh, geez.
Or in other words, ACM is equal to 5/7. 5/7 g sine of beta. So if we were rolling an object down the hill that had no moment of inertia, then that just goes down g sine of beta, right? If it were just sliding, it would have been g sine of beta. We've done a ton of problems like that. We did like a box on a ramp sliding down the ramp. And its acceleration down the ramp was always just g sine of beta.
Yeah.
Taking it to the rotation now has to make it go down some. And so if it was a solid ball, then it makes it go down, so it's only 5/7 what it would have been before.
So you can slide something down a ramp faster than you can roll something down a ramp?
Sliding down a frictionless ramp is faster than rolling down another ramp.
Yeah, there's a huge difference there.
But yeah, friction is something
Frictionless.
down.
Yeah.
Right,
There's
so,
less friction when you roll than when you do when you slide normally.
sorry, what?
Oh, but
My intuition tells me that rolling something down a ramp is faster than sliding something that is the same weight down a ramp.
And that's because your intuition tells you that the friction you have to overcome by sliding
It's greater.
is greater than the moment of inertia you have to overcome by rolling.
But if they have both the same friction, then sliding it is faster.
no.
They don't have both the same friction.
Oh.
It's rolling because one has friction and the other doesn't.
Yeah.
So if it didn't have friction, it wouldn't roll.
Right.
So you're thinking if you slide it with friction, it's going to move
Take
slower
longer.
than will rolling with friction. And it will.
Okay.
Okay. So that ends that oh wait. We found the acceleration of the center of mass.
Now we need to find the friction.
That was this. And then we need to find f sub s. So we have s sub s right here, so we can just plug in. So what's 2/5 times 2/3?
4/15.
4/15. So this is going to be equal to
Do we know n?
4/15 mg.
This is good.
That's what example was that?
7.
7.
Just make sure we're not making mistakes. So acceleration of the center of mass, we got 5/7 g sine of beta. Force of friction. Oh. That was a different problem.
What?
This was hard.
Oh, yeah, that was it.
Not that. Okay. So sub in the right thing and we'll probably get the right answer. So subbing this in now for the acceleration of center of mass. So 2/5 times 5/7 is
And 35ths.
or 2/7.
37.
Just let the pi's go out, right?
Oh, yeah.
And then we still have our mg sine of beta.
Yeah.
Okay, and now for that 2/7 mg sine of beta. Okay, good. All right, ready for work.
Of course.
Okay. We're getting through this faster than I thought.
Work and torque.
Is this angular work now?
I'm understanding this better.
This is the work you have to do to get something spinning, is one way you could think about it.
Is it not what torque is?
No, torque is the force.
Oh.
How do you do work with a force? You gotta apply the force over a distance.
Yeah.
That's how you do work.
It's just different.
So it depends on both of them. So going back to our basic definition of work. Work was the integral of your force vector dotted with your little displacement vector. Because remember, it's the force, remember dot product is always them being in the same direction. That's one way to think about it. Cross product is orthogonal, dot product is same.
Orthogonal.
At a right angle too.
Oh, okay.
So when you're doing torque, you want to be at a right angle.
So orthogonal.
You don't want to push into the door to open the door. You want to push at a right angle to the door to open the door.
Yeah. Orthogonal.
Yes. For work, you want to push in the same way you're trying to displace it. If I'm trying to move a car that way, it's very stupid to apply my force that way.
Yeah.
Okay. So, going back, work was equal to the force dotted with your displacement.
Okay.
Add all infinitely many of those up for your arbitrarily small displacements, and that gives you your total work. Now, if you are talking about doing work along a circular path, so we're rotating something, then ds is the same thing as r times d theta. Right? This comes all the way back from your arc length is equal to r times theta, where theta is in radians.
Didn't we do that like last
It's
time?
written right over there, but we've done that a bunch of times because it's very important to understand that relationship.
Yeah.
Okay, so ds r d theta. Good so far? Now, when we're saying F dotted with ds, what are we saying? We're saying the portion of the force in the same direction as your displacement times your little displacement.
Okay.
So that's going from here to here. Understand the substitution?
Yeah.
Y tangent, think about if we're on the edge of a circle. The particle's moving that way, so your little ds is that direction, right? And that's also the direction of your tangent force. Tangent to the path. So that's why F tangent. So we're good with this? Now ds is the same thing as r d theta. And what is F tangent times r?
That's your
Torque. And since we're doing it as a d theta now, we're doing it from some starting angle to some ending angle.
Okay.
Good?
Okay.
Now, in our simplest case, where torque is completely constant, so if my torque isn't changing, I'm applying a constant torque, I can pull the torque out of the integral.
Right.
And what's the integral of d theta with respect to theta?
Okay.
Theta.
It's just theta. And so this is just equal to theta evaluated from theta 1 to theta 2.
Which is delta theta.
Or theta 2 minus theta 1, which is delta theta. So if your tau, if your torque is constant, then your work, your work done in rotating it is just torque times your angular displacement.
We have another.
And that's why your torque is in like the same, it's not written in joules, but it's
It helps the units make sense. And now this is joules. Even though that's the same units as torque.
Do we have a special word or like thing for work done in an angular thing? Or should we just say?
Oh, I don't know. We'll just call it the work done to do the spinning though. Well, we'll just specify when we care about it.
Okay.
Okay, so there we go. Now, more generally, if tau is the net torque and I is some constant, the moment of inertia of the object isn't changing, then our total work done by that torque is just equal to the integral of the torque d theta, right? The torque now can be rewritten as I times alpha, where now maybe the alpha is changing. So remember, we're now not assuming that the torque is constant, but at the very least, the moment of inertia is constant. Our object isn't changing shape, or we're not changing the axis of rotation. But maybe we're applying bigger torque than small torque, then big torque than small torque, and we want to find the total work done. So we're no longer assuming torque is a constant, we're assuming moment of inertia is a constant. It's like when we went from assuming force was a constant to just the mass was a constant. You're not changing the mass of the object as you do work, but maybe you change the force. Okay, so torque can change, and the way our torque is changing is by potentially changing the alpha, the I staying constant. What is alpha by definition?
Angular over r.
It's angular acceleration, but it's the derivative of angular speed with respect to time.
Or that, yeah.
So it's the derivative of angular speed with respect to time. That was its exact definition.
Yeah.
Now, because we're not in a math class, we do the whoop-de-loop,
Okay.
and away we go. We put the dt with the d theta. And what is d theta dt?
D theta dt is.
By definition, that's your angular speed. It was the derivative of your angular position with respect to time.
Yeah.
And so now we got this as an integral with respect to your angular speed.
And I is constant.
I is constant. So we can pull the I out. And what do we get? Let's evaluate this. Pull the I out. What do we get? So we get I on the outside, and we're doing the integral of w dw from omega 1 to omega 2. So I'm starting to ending 1.
1/2 w squared.
Yeah, so this is going to be equal to, we got our 1/2 omega squared evaluated from omega 1 to omega 2, right?
Times I.
Times I, thank you. 1/2 I times that. So, when we perform that integral, we get 1/2 I omega squared evaluated from omega 1 to omega 2, which is just equal to 1/2 I omega 2 squared minus 1/2 I omega 1 squared. What is that? What is this quantity? What does that mean? Where have we seen that?
That looks like your kinetic energy.
That looks a lot like kinetic energy to me. And so that is equal to your change in rotational kinetic energy.
Which makes
So we did the exact same thing, the work energy theorem. Maybe that sounds familiar.
That does sound.
For linear work, we'll call it. And now we see there it is for angular work. And so it still works out. And so we can still keep on using the equation that we know and love, which is U1 plus K1 plus the work into the system is equal to U2 plus K2. So we're justified in still using this equation because the work energy theorem also works for this rotational work that we're talking about.
Which makes sense.
Which makes sense. So we love that equation, we'll always use it. Never goes away. Okay. Now, a work, the most general way that we can write out what work is, maybe I'll scribble it here. Work is always and forever, in its most general form, is just the integral of all the infinitesimal small works. Take an infinite sum of your infinitesimal small works, that gives you the total work.
Okay.
Right? So whatever we put here is an infinitesimally small work. So in other words, I can write an infinitesimally small work is equal to tau d theta. Why? Because that's one of the ways that we calculate work.
Okay.
You also just think about this as coming from the fundamental theorem of calculus. If the integral of this gives me that, then the derivative of that gives me that. So that's the other way that you can see where it comes from. So dw equals tau times d theta. Now you remember our definition of power. Our power was the derivative of work with respect to time. Intuitively, what's power? It's how much energy you're using per second. It's how much work energy, it's how much work energy, whatever you want to call it, per second. That's your power. It's your change in work with respect to time.
That's right.
And so now, what is dw? Well, that's tau d theta. And dt is still dt. And what's d theta over dt?
Angular.
Omega.
Omega.
So here you go. Here's your power for something rotating. Just remind you of something we already did in the past. I can't remember if this was last time or the time before. But we said dw is equal to f dotted with ds. Where did we get that? Right here. And so from that we said power, dw dt, was equal to, making this substitution now for dw, gave us our force dotted with our velocity. So you've calculated power that way before. Here's another way to do it now for rotational cases. And always and forever, you can get power as just the derivative of work with respect to time if you know what the work is in general.
Okay.
So good? See the relationship between those two equations? Probably should have written those two in our initial table as well. Power in the linear case, power in the angular case.
Yeah, they're related.
Alright, so now, here we are, we're looking at a bird's eye view of some big giant grindstone, and it's circling around. We got some machine that gets this thing going, so initially it's at rest, we turn on some machine that somehow, some way provides a torque of 9 on the sink.
9 Newton seconds.
Yeah, 9 Newton meters.
Newton meters.
So somehow we turn it on, maybe it's through the shaft or whatever, but whatever's going on, it's now applying a torque of 9 Newton meters to this thing to get this grindstone turning.
Yeah.
The grindstone has a moment of inertia of 2, so I guess it's a really small grindstone.
2.
Yeah, we calculated it all out and it came out to 2.
So it's like a weird shape.
No, it just has whatever the radius is when you calculate it,
Oh.
the 1/2 mv squared of it all, not the 1/2 mv squared. So the 1/2, assuming it's a solid cylinder, then the 1/2 mr squared, whatever it was, came out to 2.
Okay.
Okay, so it's initially at rest. We turn on our machine to get it turning, which provides a torque of 9 Newton meters. After 8 seconds, our question was, what's the kinetic energy of this thing?
Kinetic final.
And how much power was used in that 8 seconds?
Okay.
Understand the question?
Yeah.
So we got our torque, and our torque's now being applied. I need to find what's the initial kinetic energy of the thing is just 0, because it's not moving initially. I need to find the kinetic energy of the thing after 8 seconds. So I'm looking for its ending kinetic energy. What's K2? Well, I know what K2 is. That's equal to 1/2.
1 second. I'm so close.
Moment of
MV
inertia.
Or, yeah, mv center of mass squared plus 1/2 moment of inertia angular.
1/2 moment of
Angular
inertia
velocity
times
squared.
omega squared. Ending omega squared.
Why aren't we adding the other side?
Because we're not moving literally.
We're not moving it linearly, it's just spinning.
Oh,
So we turn it on and it starts spinning. There's its kinetic energy.
okay.
Yeah.
Legit.
Oh, I think we were actually supposed to find the power first. So let's start by finding the power.
Oh.
The average power. So to find the average power,
Wait, no, we need the work for the power.
exactly.
So why don't we figure out the kinetic energy first?
We're supposed to make that connection as a separate thing. So we're supposed to calculate the work using what we just did.
Oh.
But we could do what you're saying. Okay. Anyways, so our average power, P average, is equal to the total work we did divided by the time. Right? That gives us the average. So we gotta find out the work that's been done over these 8 seconds.
Yep.
Now I know the torque. What do I need to figure out the work?
Your angular velocity.
Not my angular velocity, I need my
Angular displacement.
angular displacement. I need my
Well,
Theta.
delta theta.
that's right.
Because my torque is a constant.
Oh, yeah.
Your eyes.
So I need delta theta. How am I going to get my change in theta?
Your S equals R.
This is probably kind of a leap, but see if I can get you to see it. So if torque is 9 and moment of inertia is 2, what's my alpha? Was the torque 9 on this or 10? What example are we on? 8?
8, yeah.
Okay, the torque was 10. It just keeps it a little bit nicer. Okay, so if my torque is 10 and my moment of inertia is 2, what is my angular acceleration? 5. Remember, angular force equals angular mass times angular acceleration. There's one way to think about it.
Okay.
Okay. Now, angular acceleration is equal to 5. 5 is
Big number.
Constant?
it's a what?
Constant?
A constant.
Oh.
And so what equations can we use when our angular acceleration is constant?
Your
our kinematic version of angular ones. So I can use my ending theta. I can use the fact that theta 2 is equal to theta 1, our initial theta,
Oh, that's right.
plus omega 1, initial omega times t, plus 1/2 alpha, son of a gun,
Squared.
alpha t squared. Move the theta 1 over here, so theta 2 minus theta 1 is exactly what we mean by delta theta, is equal to, what was my initial speed?
0.
0. And so it's just equal to 1/2 alpha times t squared. A times 8 is 64, divided by 2 is 32, times 5 is?
160.
And so my displacement in 8 seconds, that thing has moved an angular distance of 160 radians. So now, what is my work?
Torque is torque times that. So 160 times
10.
where's the other?
1600.
10. So 1600.
Perfect.
600 joules.
1600 joules. And now, what is our average power?
1600 over 8.
That's going to be our work over our time, which is equal to
200.
what?
200.
200.
Where did you get that?
200
Oh, 8
watts.
by 1600.
700 divided by 8.
Okay. Now, really quick, we know that alpha is 5. Scribble that over here. Alpha equals 5. What is our final angular speed then?
It is
Final velocity is equal to
18.
initial velocity
Which is 0.
plus
Your acceleration times t, right?
alpha t.
It's 5t.
So what's 5 times t?
40.
40. So I now know that omega 2 is equal to 40. So now let's find our ending kinetic energy. 1/2 times 2 is
1.
1 times 40 squared is
40 squared.
Yeah.
1600.
1600. Da, 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 da. The work matched the kinetic energy. Who would have thunk? So all the kinetic energy went into turning that thing.
I don't know when to slow it down.
Good?
Okay.
Alright. Now your favorite part.
Angular momentum.
Angular momentum. Very hard to get good intuition for angular momentum. But here's its definition. Your angular momentum is equal to your radius crossed with your momentum.
Oh.
What?
That's what it is by definition.
Momentum of what? Your particle?
Yeah.
At a point? Okay.
For a particular point mass.
What about for a rigid body?
You'd have to add it all up.
Okay. Up to there. Oh, that makes sense.
Yeah, so we'll get to this is how you do it for a rigid body in general, but just introducing our basic definition so far.
Okay.
With me? Now, it's so hard to get some good intuition for this. So if I've got this particle moving in a circle, we'll say for now, around, here's the center, here's a particle, it's going to have momentum. Its momentum vector is going to be pointing that way, and its position vector r is going to be pointing that way.
Yeah.
And so your angular momentum, it's the cross product of those, and so it's going in the same way as your omega vector is pointing. So it's pointing out this way.
Okay.
And it's, in a sense, it's how much you're rotating. It's your rotating momentum.
Counterclockwise.
So it's going to be out of the whiteboard, typically positive when it's counterclockwise, and into it. If our momentum was that way, then we'd be spinning counterclockwise, and our momentum would be into the whiteboard. Or, yeah, our angular momentum would be into the whiteboard. Okay?
So you just use a hand rule.
Use the right hand rule for when you're calculating cross products. Okay. Now, I told you that the counterpart to this is just like regular momentum. To go back to regular momentum, what was regular momentum's definition? It's just mass times velocity, right?
Yep.
Mass times velocity.
I do that.
And so what do we get when we take the derivative with respect to time of momentum?
You get your force
then yeah. So if we took the derivative of time with respect to that whole thing, then we would get m times a. Or in other words, we get our force vector.
Yeah.
Oh. Yeah.
So a force is a change in momentum. What do you think our derivative of angular momentum is going to be? Our angular force, or torque. So what is the derivative now of angular momentum with respect to time? So we got to take the derivative of this thing or that thing. I'm going to write this one here. That's what we're taking the derivative of.
Okay.
So we're taking the derivative of this. Now you got to remember back to how you do derivatives. When you take the derivative of the product of two things, what was it?
Chain rule.
No, it's the.
Not the chain rule, it's the product rule.
It's.
When I take the derivative with respect to t of g of x times f of x,
It's the derivative of. It's for the first
Oh,
time.
the first
derivative
and
of
the
the second.
second.
I
That's the
know
derivative of
that
the
there's
first.
a high low one, yeah, but that's.
okay, perfect. So the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. This is a product, and we didn't prove that that's the way that derivatives work on these things, but that's the way derivatives work on these things. So it's the exact same thing, so we have to do a product rule. So what is the derivative of your position vector with respect to time?
It's your velocity.
It's your velocity vector. So the derivative of the first multiplied by second plus the first times the derivative of the second.
Which is.
Oh, that's right.
Yeah.
Oh yeah. I get.
Okay, now focus on this term for a second
I remember.
and tell me why we love that term.
Because it is.
Oh, because it's m times velocity squared, which is
No, that's a cross product.
Cross. MV.
So you got a vector crossed with a vector.
But it's your velocity crossed with your momentum.
Sure, but which way does velocity point? Let's say it points that way.
Okay.
Which way does this velocity point?
in the same direction.
Same direction. What's a cross product of two vectors pointing in the same direction?
It's just the
How orthogonal are two vectors in the same direction?
They are.
They're zero orthogonal.
Yeah.
So they are. So you do the back part.
so there's 0.
So this term is zero.
Oh.
That is what I was trying to hint at in
Okay.
some way in failing. Remember that with cross products, we think it gives us how orthogonal they are to each other. Dot products give us how parallel they are to each other.
Oh.
Cross products are how orthogonal are they to each other. Those are not orthogonal at all. Or that times the sine of the angle between them. What's the angle between those two vectors?
0.
Zero. So,
Gotcha.
okay, so that term goes to 0, and so we're just left with this term. R crossed with MA. What is MA?
Force.
Force. R crossed with force is our exact definition of
Work.
torque. Holy camole. It worked.
Wow.
And like we already said before, the derivative of just regular momentum with respect to time was force. The derivative of angular momentum with respect to time is torque. So force produces a change in
Torque.
linear momentum. Torque produces a change in
Angular.
angular momentum. You want to change your angular momentum? You need a torque. You want to change your linear momentum? You need a force.
Good job.
Okay,
Rigid-Bod.
so now the angular momentum of a rigid body. How are we going to do this? We're going to calculate the angular momentum of all the point-like masses of this rigid body as it's rotating and add them all up, and that's going to give me the total angular momentum. Good? So let's go ahead and do that. By definition, so here's the center of mass, here's what's rotating about, that's our axis of rotation, some crazy rigid body. Looking at the angular momentum of that point mass right there. Good? Okay, so we're going to call that L sub I. What is that equal to?
Well, it's the cross between your radius and your velocity.
Perfect. The cross between your radius and your momentum, or your radius and your velocity with the mass, scaling it up. So you get the mass in there. But my radius and my velocity, if this thing is just spinning around some center of mass, those are always going to be perfectly orthogonal to each other. Right? When you're moving in a circle, the motion along the edge of the circle is always perfectly tangent to the circle. It's perfectly orthogonal to your radius. So the sine of the angle between them is always going to be 1. So we don't need to count that. So the magnitude of your angular momentum then is just going to be R and V, all multiplied together. You see all that? since it's angular momentum, then your velocity, since we're just talking about in a rotating case, your velocity can be rewritten as omega times r.
Okay.
And now this omega is just how the whole rigid mass is spinning. This omega does not depend upon which point particle you choose. If this point is rotating around the center of mass at 2 radians per second, so is this point.
But the radius is smaller.
It doesn't matter. If this point completes a rotation once every second, then this one completes a rotation once every second. Its angular speed is the same. Their linear speeds are different, and so the v sub I is different. But their angular speeds are the same, so that omega is going to be the same for every single one of those point masses.
Right.
Okay, so now the total angular momentum is going to be a sum of all those little angular momentums. We have the mi, we have the r sub I squared, and we have the omega. And m sub I times r sub I squared is exactly what we mean by the moment of inertia of that mass. Sum it all up gives me the moment of inertia of the entire thing, and we just factored the omega out. So that gives you the magnitude. They're all moving in the exact same direction since it's all rotating in the same direction. So if you want it as a vector, here it is as a vector. And that doesn't change anything. Good? So there's a definition. We showed that this falls out from that definition for a rigid body. Good so far? Okay. Now we have conservation of angular momentum, the same way that we have conservation of linear momentum. How do we know that? Well, we know that what is a change in angular momentum with respect to time equal to?
Torque.
The torque. And so if the net torque on a system is 0,
Then you're
if the derivative of something is 0, then that function must be a
Constant.
constant. And so that means that our angular momentum is a constant. And all the internal torques inside of the system cancel out. The same way we did this with internal forces.
yeah.
Because if the forces cancel out, the torques are going to cancel out because it's the same radius between the two particles exerting the force on each other.
Right.
Yeah.
So they have the same radius, the forces are equal but opposite, so the torques are going to be equal but opposite. So all the internal torques cancel out, it just matters what the external torque is, and if the net external torque is 0, then it's constant. Okay, so with that, let's move on now to more examples. What's the last example we did? 8?
Wait.
So we're starting at 9. So I'll flip it over here and pop up the projector so that we have you can read the problems. Okay, that's got it pretty good. Can't really get any good distance in between. Is that bigger? Alright, I don't know why it's at such a weird angle. It keeps messing with the settings. Alright, but now I get messing with it. So let's just do this example now. So a turbine fan in a jet engine has a moment of inertia of 2.5 kilogram meter squared. So our moment of inertia is equal to 2.5. About its axis of rotation. As the turbine starts up, its angular velocity is given by omega. Now they're saying it's omega in the z direction. So it's coming out of the board is the way that you're thinking about that. But our omega is equal to 40 times d squared, right?
Why is it seconds cubed?
Radians per second cubed, they're just keeping track of their units. When you do it times squared here, that's going to give you seconds.
Oh,
And so you're going to get radians per second, which is what omega is.
I see.
So that constant right there is radians per second cubed. I don't bother writing the units when I write these equations. I think it just makes a mess. Okay. And they probably have a picture of the thing. No, they don't. We don't really need a picture then. So A, find the fan's angular momentum as a function of time. So we're going to think about its angular momentum. I'll put a T here to remind us that we're thinking about as a function of time. What is the angular momentum now of a rigid body?
L equals vector r times vector p momentum.
It's the cross product between your radius and your linear momentum.
It's what?
Equals vector r times
I'm talking about angular momentum.
Angular momentum for a rigid body. It's the last derivation we did.
Ah,
Second to
it's
last.
the moment of inertia times zero.
It's the moment of inertia times your angular momentum, or your angular speed, I mean. What's 2.5 times 40?
80, not 100.
100. So it's just 100 t squared, okay?
Okay.
That times that for it. Good?
Yeah.
Okay. Now, so there's that. And what's its value at t equal to 3? So what is our angular momentum after 3 seconds of this turbine spinning?
900.
900.
900 meters.
900, let's see.
Joules.
How do we get this? We take
Moment.
radius times momentum. So you have kilogram meters squared per second. So kilogram meters squared per second.
Which is that unit that we use?
Nope. Not that I know of. We can see what he gives it as.
For around here per second.
So there's that. Let's see, part B was find the net torque on the fan as a function of time. So now we're looking for the torque as a function of time. How is torque related to angular momentum?
It's the derivative.
It's just a derivative. So tell me my torque.
It's 200 t.
200t. What's my torque at time 3?
600.
600
It's the derivative.
Newton meters. Yeah, torque is a derivative of angular momentum, the same way that force is a derivative of linear momentum. So that's what we did at the top there on the note. So definition of angular momentum, then I got my note there. And I took the derivative of it, and we got torque.
Okay.
Okay, so there's 10.9. 10.10. Okay, I think I remember how this one works. Okay, so 10.10, we got a physics professor, and he's standing on, so here's our guy. He's going to be holding 2 dumbbells, outstretched like that. And he's very happy to be doing this. And he's standing on some platform that is spinning around frictionlessly. Good? Now, what he's going to do is he's going to pull in those dumbbells. As he pulls in those dumbbells, what's going to happen?
This moment of inertia is bigger.
He's going to start spinning quicker. You've seen this all the time, like ice skaters pulling their hands in, and they start spinning quicker as they pull their center of mass in.
Yeah.
Or as they pull their mass in, not their center of mass in. So that's what we're going to see happening in this problem. So we're going to start with the initial case. He's going to have them out, and he's going to pull them in.
Okay.
So let's look at our angular momentum at the start. Our angular momentum at the start is going to be his moment of inertia at the start times omega 1. So we'll need to get his moment of inertia at the start and his moment of inertia at the end. And then his angular momentum at the start will be that times his initial angular speed. And his moment of inertia at the end will be his second moment of inertia. Am I just repeating the same thing twice? I think you know what I mean, but I think I said it wrong. His angular momentum at the end will just be his moment of inertia times his second angular speed. These have to be equal to each other. Because angular momentum is conserved.
Yeah.
And so I know that we're going to be solving for omega 2. So I'm going to have his initial moment of inertia times his initial angular speed is equal to his final moment of inertia times his final angular speed. Those moments of inertia are going to be different because he's going to pull in his arms. So as his moment of inertia gets smaller, his angular speed is going to get bigger. And so finally we're going to get his angular speed is going to be equal to I1 over I2 times his initial angular speed. So let's calculate all these. So first off, his initial moment of inertia. So they tell us, with his arms spread out, his moment of inertia is 3. Now we need to add the moment of inertia of each of the dumbbells. When he's reaching his arms out, each dumbbell is
1 meter?
1 meter. Oh wait. So what is the moment of inertia of this dumbbell if it's spinning around his axis?
That's 5.
It's 5 kilograms, and it's 1 meter away.
So that's 5 kilograms.
So it's just going to be 5 kilograms. Writing it all out, it's going to be the mass times the radius squared. And we have that twice for each of the dumbbells.
Yep.
For a total of
13.
13. Okay, down here, it tells us that when he has his arms tucked in, his moment of inertia is 2.2. And when he has his arms tucked, 2.2, not 2 times 2. And when he has his arms tucked in, the dumbbells are only 0.2 meters away from him now. So I have 2 dumbbells. They each have a mass of 5, and their radius away from him now is 0.2 meters squared. So 0.2 times 0.2 is
0.2
0.04 times 10 is
0.4.
0.4 plus 2.2 is
2.6.
2.6. Okay, so there's his final moment of inertia. His initial and his final. Now, what was his initial angular speed? They said he completes a revolution in 2 seconds.
Okay.
So he goes 2 pi radians, full circle, 2 pi radians in 2 seconds.
So he goes half a radius.
So 2 pi radians in 2 seconds, or in other words, pi radians per second. This is his angular speed. So then, when he tucks his arms in, what's his final angular speed? It's going to be 13 divided by 2.6,
Times 5.
which is going to be 5 times pi.
4, 5, 5. Wait, 5.
Yeah. So 13 times 2 is 26. Divided by that is 10. And then I multiply by 2, so now divide by 2.
Really?
So he's spinning around 5 times faster pulling in those dumbbells.
That's cool.
Okay. But now let's think about the kinetic energy. Energy didn't go anywhere, right?
No.
So what is the initial kinetic energy? It's going to be 1/2 I1 times omega 1 squared. Right?
Yeah.
Which is going to be equal to, omega 1 was pi, I1 was 13, so it's going to be 13/2 times pi squared.
Yep.
What was his final kinetic energy? Once again, same exact formula. 1/2 times 2.6 times pi squared.
It's going to come out to the same. Wait, what?
Well, this is going to be equal to 1.3 times pi squared.
Pi squared.
This one is equal to 6.5 times pi squared.
Wait, that's a big enough.
So this one is equal to 6.5 times pi squared.
Well, there you go.
13 times 5 gets you 65, right?
Yeah.
So it's 5 times as much energy.
The one in the
Double
spin
that.
5 times as fast.
So I have one kinetic energy.
And then you,
I have 5 times more.
Yeah. How'd that work?
Now it's less. Now it's more.
Well, your momentum is conserved.
Where's the energy going?
Story errors or torque.
Well, then it would be my angular kinetic energy. All our energy is in spinning.
Yeah. Well,
How do I have more energy when I pull my arms in?
Your momentum is
Where'd that extra energy come from? Let's use our always and forever equation. U1 plus K1 plus W.
You put work into moving the dumbbells.
Aha, there you go. I had to do work pulling in the dumbbells. Right? If I'm spinning, is it harder to move an object towards you or away from you?
Away. It's hard to move towards it.
Towards you. So I had to do a lot of effort to pull those dumbbells in, which got me spinning faster.
Uh-huh.
And now I can let the centrifugal acceleration do work of pulling it back out, slowing me down.
So it's like potential energy kind of?
So it's kind of like potential energy. That's one of the things that they use in a lot of sci-fi-like designs for things is using a flywheel to get something going versus getting something moving versus slowing it down. And basically, it's an idea of having some big heavy object that's spinning. As it increases its spin, well, it's not quite the exact same as this. That's your angular momentum. Never mind.
Is there a concept of angular potential energy?
But there is a way that you can view that as like a potential energy, storing it up, letting it go.
Do we define angular potential energy at all?
Now. Okay. So, fun problem, mostly because of the energy. It's easy to,
Get lost.
lose track of your energy there. Okay, here's a very simple one. So, I got some gear, and I got my clutch that's going to hook onto it. We're going to pass over the details of how it hooks onto it.
Okay.
But initially, this has an angular momentum, this has a moment of inertia, I sub A. This has a moment of inertia, I sub B. This is spinning around with omega A, this is spinning around with omega B. Once I connect them together, what is my new angular speed going to be? So let's track the angular momentum. What's the angular momentum of this? I sub A times omega A. What's the angular momentum of this? I sub B times omega B. Now, when I connect them together, then my new moment of inertia is just going to be the sum of the moment of inertias. And then they'll have some new angular speed, and the question is, what's that new angular speed?
Yep.
And how do you solve it? You just divide both sides by the moment of inertia. So your angular speed is just going to be I sub A I sub A times omega A plus I sub B times omega B all over I sub A plus I sub B. You've seen almost this exact equation when we were dealing with momentums. When we were talking about objects colliding in a completely inelastic way, then we said the mass of object A times the velocity of object A plus the mass of object B times the velocity of object B is equal to the mass of A plus the mass of B times our new velocity. And how do we solve our new velocity? Just divide. So exact same thinking. Good?
Yep.
Just really quick look at theirs in case we did anything stupid. Drag it down so that we can actually see it. So, same exact thing, right? Sorry, with the text there. But yeah, it's the same. You can take my word for it. Okay, our last example problem. So we can actually read it. So let's see, we've got a door. That doesn't raise good. I'll try and keep it here. Use green for my door and then go from there. So bird's eye view looking at a door. Here's the hinges on this end, and then here's the actual door. Good? The door has a radius, has some r for its length. We know what the r is. It will give it to us somewhere in the problem. And we've got a bullet flying into the door. So a bullet is coming out the door. It's got its little mass, and it's flying this way with the velocity of the bullet. And it's going to penetrate itself into the door, into the center of the door. Our question is going to be, what is the angular speed of the door that this is going to open with? So, we know r, the radius of the door. We know the mass of the entire door. We know the mass of the bullet, and we know the velocity of the bullet. And with that, our job is to try and figure out the angular speed that this thing opens with. So we're trying to figure out what omega is. Everything there makes sense? Okay, so we're going to have to use conservation of angular momentum.
So it is considered kinetic energy.
Not kinetic energy, angular momentum is conserved. So what is our angular momentum the instant that the bullet hits the door? The instant that the bullet hits the door, everything that is providing movement to the system is just that bullet and where it hits.
Yep.
right? So the instant it implants itself in the door and it hits right there, then its angular momentum, L sub 1, is going to be equal to the mass of the bullet times its velocity. Or sorry, we just did the line for the mass of the bullet, times the velocity of the bullet, times it's completely orthogonal.
So those one.
Times the sine of the angle between them is 1, times, what am I missing?
No.
Which equation again?
The top one, the definition of angular momentum for a point mass.
Your mass of the bullet.
The radius.
Radius. Okay.
Where it hits the door. Because think about it. If I were to shoot a bullet right into the hinge, how much would that open the door?
No.
Not at all. If I shoot the bullet down here, it's going to do more. So the radius very much matters for your angular momentum. What the momentum of the bullet was matters, and where it hits the door matters.
Right. Yeah.
So that's where our R over 2 comes from. R over 2 because half the width of the door. Where R is the width of the door. With me so far?
Yep.
Okay. So there's our angular momentum at the start. Our angular momentum at the end now is going to be the angular momentum of the entire rigid body. So our angular momentum at the end is going to, we have to use I times, what?
What's the capital one?
Omega, right?
Omega.
That should be the intuitive one.
Yeah.
What's linear mass, or linear momentum? Mass times velocity. What's angular momentum? Angular mass times angular velocity.
Angular mass.
Sure, that's the way to think about it sometimes.
Yeah.
Yeah.
Your angular resistance, your resistance to angular motion, angular mass. Okay. Keep in mind, all these equations, they've got two forms. Right? We had our equation for torque, which was the angular way of thinking about it. And then we had our equation with torque, which related it to linear force. Same thing with momentum. We have our equation for angular momentum. L is going to be just P times R. That's going to be how you relate linear momentum to angular momentum. And then L is going to be our angular mass times our angular speed. And so all of these are going to have those two types of equations.
Yeah.
The angular version, and then how it relates to the linear version, typically multiplied by R. Okay, so here's our angular momentum at the end. We need to figure out what that I is. That I is the moment of inertia of the door, and it's also got that bullet embedded in it. Now that bullet's not really going to make much of a difference, but we'll keep track of the bullet anyways to see that it makes no difference. Okay, so what's the moment of inertia of the door? Now we've already done this, you probably don't remember. A thin mass rotating about one of its ends back when we calculated moments of inertia in that table.
Your rod?
Not the rod. It's one that we didn't actually calculate. Sorry. I told you that we couldn't do this actual one. It's one I wanted to, but we didn't have time for it.
Oh.
Because we're thinking about the door as a rectangular prism, thin rectangular prism rotating around that mass.
Yeah.
So it is just, do I dare just guess? I think it's 1/3. The mass of the door times the radius squared. I don't know if any of you have that table quickly. Actually, they'll just tell us. MD squared over 3. Okay, that's right. So there it is for the door, and then let's get it for the bullet. The bullet is going to be plus the mass of the bullet times its radius squared, because the bullet's just a point mass.
R squared over 4?
So R squared over 4. Because where it hit, squared. Where it hit is R halves squared.
Yeah.
Okay, so there is our moment of inertia, and now we can plug in all the numbers that we know for these things. So we have 1/3 times, what was our mass of our door? 15. Times the radius of our door, what was its length? Was it 1 meter?
It was 1 meter wide.
Yeah, 1 meter from here to here, so that's what our R is. Okay, so that's just 1, we don't have to worry about that. Plus now, oops, like a times. Plus now, the moment of inertia of our bullet. What's the mass of our bullet?
10 grams or.
So 0.01 kilograms
Yes.
times R is just 1, so that's just times 1/4.
No. R is.
R was the length of the door.
Okay. Oh. Okay.
Okay. And so that comes out to 5.0025. That 0.0025 part is coming from the bullet, the 5 comes from the door. And so, since we're only going to end up having what? 2 significant figures, you can see that the bullet's not going to matter.
And this is in kilograms meters.
That is kilograms meters squared.
Okay.
Okay, so there's I. We were looking for omega here. So I've got I in my calculator. So I know that this is equal to this. So I know that the mass of the bullet times the velocity of the bullet times R over 2, or in our case 1/2. So this is equal to I times omega.
Yeah.
Or in other words, omega is going to be equal to the mass of the bullet times the velocity of the bullet times 1/2 all over I. And we'll see what that equals. I still have I stored in my calculator, so the mass of our bullet, that was 0.01 times the velocity of our bullet, what was that? 400
400 meters per second.
times 0.5, all divided by our moment of inertia gives me 0.3998 or 0.4. So it's going to be 0.40 radians per second will be our angular speed. So that's how fast it will start opening,
Which isn't super fast.
which isn't particularly fast. What's a radian? Roughly, think about a radian as 60 degrees. So this is roughly 24 degrees after a second.
Wow. Okay. So it kind of opens up a little bit.
It opens up a bit. With it being completely frictionless hinges, shooting the bolt into the door.
Interesting.
Okay, let's calculate the kinetic energy at the start and the end of this.
Okay.
What is the kinetic energy when we have just a bullet? So our starting kinetic energy is just a bullet flying through the air.
Yeah.
So our starting kinetic energy
0.01 times.
is just equal to 1/2 m velocity of the bullet squared, right?
Yeah.
Which won't bother being clever about. So 0.5 times 0.01 times 400 squared is equal to 800 joules.
Okay.
Now, what is our kinetic energy at the end? So now all the kinetic energy is just going into the rotation of that thing.
Close the door. Yeah.
And so that's just going to be 1/2 I times omega squared.
Yeah.
So 0.5 times I still have I stored here, times omega squared.
What is it? 0.16.
And so you get 0.4002, or essentially, this is basically 0.40 joules.
Wow.
We went from 800 joules to nothing. The energy's gone. Where'd it go?
Into rotation.
It disformed the door in front of me.
Only 0.4 joules went into the rotation of the door.
You blew the door.
So the rest of it went into what?
Blowing up the door.
Blowing up the door?
You disformed it and you heated it up.
Yeah, the deformation of the door, breaking it up, and
Embedding.
embedding itself, and lots of heat coming off of that.
Yeah.
So lots of deformation. That's another way you can think about it back with the professor pulling in his arms. That was like a deformation to the rigid body.
Oh, that's kind of a cool way to think about it.
So, energy completely gone, basically.
Yeah.
Angular momentum sticks around.
Will we get to talking about the actual deformation and heat in this class?
We will talk about heat. Capturing deformation, that's a very difficult thing to do because it's so messy. But we will have a lot to say about heat. Our final 3 sections will be on thermodynamics. Our final 3 chapters.
Is there a way of modeling a system where the shape of the system changes? So
Probably.
like where the moment of inertia is changing while you're rotating.
I'm sure. I don't know what it is. I would guess it would be an absolute nightmare. Just always remember how easy it is to talk about this without air resistance, and then just add it proportional to the velocity. Right? It makes a night and day difference. So you start introducing some of these changes and things blow up. Okay, wow, that is it. I cannot believe we are done.
I can.
Okay, so that's all there is for that. We'll see you guys.